Hi everyone, and welcome to the second of two videos going through some past exam questions on enthalpy changes. So in this question they've given us a reaction here. We've got hydrogen and carbon dioxide reacting together, that's fine. So it says 49 kilojoules of energy are released when 3 moles of hydrogen react completely. This is the enthalpy change of reaction. Calculate the energy released when 1,000 decimeters cubed of hydrogen, measured at room temperature and pressure, react completely with carbon dioxide. Okay, so they've given us here the volume of the gas. So the key bit of information we need to use is the fact that we have this relationship where every time you have 1 mole of gas, its volume is 24 decimeters cubed. Okay. So the key thing here is where it says at room temperature and pressure. That's what tells us that we can use this relationship, that it's 24 decimeters cubed per mole of gas. So what we can do then is, if we take the volume and divide it by this, that's going to give us the number of moles. So we can do 1,000 decimeters cubed divided by 24 decimeters cubed per mole. And that's going to tell us how many moles of hydrogen we've got. So 1,000 divided by 24, and it's 41.7, let's call it, moles. But I'm going to keep that number on the calculator. Okay, that's moles of hydrogen. So if that's what we've got, then we know that 49 kilojoules of energy is released when 3 moles of hydrogen react. So what we want to do is we've got 49 for every 3. So if we do this number, 41.7, divide it by 3, and then times that by 49. And so, right, how many times does 3 go into that? And every time we've got 3 moles, we have 49 kilojoules of energy. So I'm going to do my 41.7 divided by 3, and then times it by 49. So I'm going to got the number that I kept on the calculator, because it's not 41.7, is it? It's going to be slightly wrong if we use that. So I'm going to use that number, divide that by 3, and times it by 49. And I get 680.5. But it says do it to 3 significant figures, so it's going to be 681. Okay. Right, the next bit says, complete this enthalpy profile diagram for the forward reaction. Label the activation energy and the enthalpy change. Okay, so we need to go back and look at, was this exothermic or endothermic? It says, it hasn't given us delta H, but it does say that 49 kilojoules of energy are released. So if we're releasing energy, it must be exothermic. So on the diagram here, the products are going to be lower in energy than the reactants. Okay, we're going to be down here, and we're going to have our delta H would be negative, because it's releasing 49 kilojoules of energy. Here we're going to want to write the products. So the products are methanol and water. So if we put those on here, just copy those from the equation. And then we need to show the activation energy, so that's going to go up a little bit first before it comes down. And then the activation energy is that gap there. It's probably a good idea whenever you're drawing these diagrams just to draw the arrows with only one arrowhead on, because we want to show that there's a direction. Okay, sometimes they get picky if you put like a second arrowhead on the bottom here, because we want to show that the activation energy is energy you have to put in, whereas the enthalpy change of reaction in this case is exothermic, so we want to show the directions. Okay, what is the enthalpy change of reaction for the reverse reaction? Okay, well, we said this reaction is releasing energy, and it was releasing 49 kilojoules of energy, wasn't it? So if it's released energy, delta H must be negative, so it would be minus 49. So therefore the reverse reaction must have an enthalpy change of plus 49. And then finally here, a scientist estimates the activation energy as plus 225. Okay, so that's this value here. What's the activation energy of the reverse reaction? Okay, so if we're going backwards, we're going this way, we're going to have to do the opposite of delta H, which we've just worked out is plus 49. So going from there up to this point would be plus 49, and then we'd have to do the activation energy as well. So it'd be 49 plus 225. Okay. So we'd have to do 49 plus 225. So it's going to be plus 274. Okay, a couple more questions here that I want to look at. So here's another diagram. We've got this reaction here between nitrogen and oxygen. They've given us an enthalpy profile diagram. It says, calculate the enthalpy change when 240 decimeters cubed of N2O is formed. Okay, so this is similar to the question that we just looked at, where they've given us the volume. Okay, so we're going to do our 240 decimeters cubed divided by our 24 decimeters cubed per mole. And that's going to tell us that we've got 10 moles of N2O. And so we can see in this reaction that when we form 2 moles of N2O, the enthalpy change is plus 164. So if we're forming 10 moles of N2O, we're doing this 5 times, aren't we? So the enthalpy change is going to be plus 164 times 5. Which is 820. And it's going to be plus 820. Does that make sense? Because this is the reaction for making 2 moles of N2O, and it's that enthalpy change. So if we're making 10 moles of N2O, we've timesed it by 5. The next bit says, what is the enthalpy change of formation of N2O? Okay, well, here, this is the key bit. You think, oh, well, it's the enthalpy change is 164, right? But that's for this reaction. Remember, your definition for enthalpy change of formation is the formation of 1 mole of a compound from its elements. This reaction here is forming 2 moles, and it's plus 164. So the enthalpy change of formation, if it's forming just 1 mole, must be plus 82. And then finally, it says this reaction is reversible. Calculate the activation energy for the reverse reaction. Okay. So this is kind of similar to the question that we've just seen. Okay. But if we go back to our diagram here, the difference here is that this reaction is endothermic. So if I'm going backwards, if I'm starting here and going that way, then my activation energy is just going to be that part there, isn't it? So this is going to be the activation energy for the reverse reaction. It's going to be from here up to there. So it's all of this minus this part. Okay, we're not counting that, so it's going to be 447 minus 164, which is 283. Okay. So that's going to be our activation energy for our reverse reaction. And again, it's always a good idea to put signs on enthalpy changes. We don't technically need any of these pluses here, but I think it's a good habit to get into, because if it's negative, you definitely do need the minus sign. So if we just always get in the habit of putting a sign on an enthalpy change, it means we're not going to miss out when we actually need to.